Welcome to Math Lessons. In this video presentation, let us discuss solving system of linear equations in two variables using inverse of a matrix. This is under discrete mathematics. Before we continue, let us have a recall of some important topics. And let us begin with the determinant of a 2 by 2 matrix. Suppose we are given matrix A with elements A, B on the first row and C, D on the second row. The determinant of A may be obtained by the difference between the product of the elements in the main diagonal and the product of the elements in the other diagonal, that is AD minus BC. Hence, if we are given matrix A with elements 3, negative 5 on the first row and 2, 4 on the second row, the determinant of this 2 by 2 square matrix is given by 3 times 4 minus 2 times negative 5. 3 times 4 is 12, negative 2 times negative 5 is positive 10. Then the determinant of matrix A is equal to 22. Next, let us recall the procedure in finding the inverse of a 2 by 2 matrix. Again, let us have matrix A with elements A, B on the first row and C, D on the second row. The inverse of matrix A is given by 1 over the determinant of matrix A times the matrix where the main diagonal are the elements switch from the original matrix A, and the other diagonal have elements which are the negative of the elements in original matrix A. So if we have A is equal to the matrix with elements A, B on the first row, C, D on the second row, the inverse of A is given by 1 over the determinant of A times the matrix D, negative B on the first row, and negative C, A on the second row. Let us have an example. Find the inverse of matrix B with elements negative 2, 1 on the first row and 3, negative 1 on the second row. This is our suggested solution. For step 1, we first find the determinant of B. So we have negative 2 times negative 1 minus 3 times 1. So the determinant of B is equal to 2 minus 3, that is negative 1. Next, we'll find the inverse of matrix B. And this is given by 1 over negative 1, that is the reciprocal of the determinant of matrix B. Then we'll have the scalar multiplication to the matrix with elements negative 1, negative 2 on the main diagonal, that is the main diagonal elements of matrix B that are switched or swapped. And the other diagonal will have the negative of the elements in matrix B, that will be negative 3, negative 1. 1 over negative 1 is negative 1, and then we'll do scalar multiplication with the matrix. So we have the inverse of matrix B as negative 1 times negative 1, that is 1. Negative 1 times negative 1, that is 1. So we have 1, 1 on the first row. And then negative 1 times negative 3 is positive 3. Negative 1 times negative 2 is positive 2. So we have 3, 2 on the second row of the inverse of matrix B. Also recall that the product between the matrix and its inverse is an identity matrix. In this case, the original matrix B is a 2 by 2 square matrix. Of course, the inverse of matrix B will be a 2 by 2 square matrix. Hence, the product of B and its inverse is a 2 by 2 identity matrix with 1, 0 on the first row and 0, 1 on the second row. This time, let us proceed to solving system of linear equations in two variables using the inverse of a matrix. Suppose we are given the system of equation a sub 1x plus b sub 1y is equal to c sub 1, and the other equation a sub 2x plus b sub 2y equals c sub 2. To find the solution to this system of linear equations, using the inverse of a matrix, we follow the equation AM is equal to B, or A times M is equal to B, where A is the coefficient matrix, A sub 1, A sub 2 on the first column, B sub 1, B sub 2 on the second column. Again, this is called the coefficients matrix. And M is the variable matrix. We have X and Y. A column matrix since we're looking for the values of X and Y. Again, this is called the variable matrix. And last, we have the constant matrix. B is a column matrix C sub 1, C sub 2. This is the constant matrix. And from here, we follow the equation. The inverse of A times AM is equal to the inverse of A times B. From the equation AM equals B, we multiply both sides by the inverse of matrix A. And since matrix A times its inverse is equal to the identity matrix, then that is equal to 1, 1 on the main diagonal. Then the values of X and Y here for the variable matrix will be equal to 1. Hence, we have the variable matrix left on the left-hand side of the equation, and then on the right-hand side of the equation, the inverse of A times matrix B. This will be our equation in finding the values for X and Y. Again, that is the inverse of matrix A times the matrix B. This time, let us have some examples. Example number 1. Solve the system of equations 4x minus y equals 9 and 3x plus 2y equals 4 using inverse of a matrix. Here is our solution. Let us do the solution in a step-by-step manner. Step 1, we write in the form AM equals B, where A is the coefficient matrix, M is the variable matrix, and B is the constant matrix. In here, M and B are column matrices. So we have the coefficient matrix from the two equations, 4, negative 1, 3, 2. Remember that before getting the coefficient matrix, we need to make sure that the two equations in the system are written in standard form. Multiplied by the column matrix XY, which is the variable matrix, equals the column matrix with elements 9, 4. These are the constants in the system of equation 9 and 4, and that is our constant matrix. Next, we'll find the determinant of A. That's the coefficient matrix. So we have the determinant of A equals 4 times 2 minus 3 times negative 1. 4 times 2 is 8, negative 3 times negative 1 is 3. So we have 8 plus 3, 11. The determinant of A is 11. Next step, we'll find the inverse of matrix A. That is 1 over 11, scalar multiplication, matrix with main diagonal 2, 4. These are the swapped elements of the original coefficient matrix for 2. And in the other diagonal, we get the negative of the elements in the other diagonal of matrix A, or the coefficient matrix. That is 3, negative 1. Then it becomes negative 3, positive 1. Doing the scalar multiplication, we have 1 over 11 times 2, that's 2 over 11. 1 over 11 times 1, that is 1 over 11. And then 1 over 11 times negative 3, that is negative 3 over 11. 1 over 11 times 4, that is 4 over 11. This time, we're going to multiply both sides of AM equals B by the inverse of A. Then we'll have AM times inverse of A equals B times inverse of A. Or we can just follow the formula. That will result to the variable matrix XY is equal to the inverse of A times the constant matrix 9, 4. Doing that, we have 2 over 11 times 9, that is 18 over 11, plus 1 over 11 times 4, 4 over 11. In the second row, negative 3 over 11 times 9 is negative 27 over 11, plus 4 over 11 times 4, that is 16 over 11. So we have the product of this 2 by 2 matrix and the column matrix as a 2 by 1 matrix or a column matrix for the values of X and Y. Simplifying, 18 over 11 plus 4 over 11, we have 22 over 11, or that is equal to 2. Next, negative 27 over 11 plus 16 over 11 is negative 11 over 11, and that is negative 1. Hence, the variable matrix XY is equal to the column matrix 2, negative 1. Then we are done. The solution to the system is 2, negative 1. X is equal to 2 and Y is equal to negative 1. Let us have another example. Again, solve the system 5x minus 2y equals 1 and 4x minus 3y equals negative 9 using inverse of a matrix. For our solution, we will not introduce anymore each step, but we will follow this step-by-step solution. We'll start with the equation of the form AM equals B, the coefficient matrix 5, negative 2, 4, negative 3. These are the coefficients in our system of equations 5, negative 2, 4, negative 3. Multiplied by the variable matrix XY equals the constant matrix 1, negative 9. And then we will find the determinant of the coefficient matrix, that is 5 times negative 3 minus 4 times negative 2. We have negative 15 plus 8, negative 7. So the inverse of A is 1 over negative 7 times the matrix whose main diagonals have element swapped from the original coefficient matrix. So we have negative 3, 5, and then the negative of the elements in the other diagonal, we have negative 4, negative of negative 2, that is positive 2. Performing the scalar multiplication for the inverse of A, we have 1 over negative 7 times negative 3, that is 3 over 7. 1 over negative 7 times 2, negative 2 over 7. 1 over negative 7 times negative 4, that is 4 over 7. And then 1 over negative 7 times 5, that is negative 5 over 7. Next, using the formula, the solution to the variable matrix xy is the inverse of A times the constant matrix. So we have 3 over 7, negative 2 over 7 in the first row, 4 over 7, negative 5 over 7 in the second row, times the column matrix 1 over negative 9. Doing that, 3 over 7 times 1 is 3 over 7 plus negative 2 over 7 times negative 9, that is 18 over 7. In the second row, we have 4 over 7 times 1, that's 4 over 7, plus negative 5 over 7 times negative 9, that is negative 45 over 7. Simplifying the result in the column matrix, 3 plus 18, 21 over 7, that is equal to 3. 4 plus 45, 49 over 7, that is equal to 7. Hence, the solution is the column matrix 3, 7. So, x is equal to 3 and y is equal to 7. Therefore, the solution to the system is the ordered pair 3, 7. This time, let us apply this solution in a word problem. Example number 3. Twice the larger of two numbers plus the smaller is negative 25. The larger minus 3 times the smaller is 138. Find the numbers. Here is our solution. Since we are solving a word problem, let us begin with representations. Let x be the larger number and y be the smaller number. So we're going to solve this word problem using system of linear equations in two variables. This time, let us form the equation from the first sentence. We have twice the larger of two numbers. Since the larger number is represented by x, that will be 2x. Plus the smaller, and the smaller number is y, so we have 2x plus y equals negative 25. Let us look at the second statement. The larger, that will be x, again, minus 3 times the smaller, so we have x minus 3y equals 138. And then from here, we will follow the solution using the inverse of a matrix. Then we begin writing the matrices. For the coefficients matrix, we have 2, 1 in the first row, 1, negative 3 in the second row, and of course, the variable matrix will be the column matrix xy, and the constant matrix, we have negative 25, 138. Next, let us find the determinant of the coefficient matrix. Represented by A, we have 2 times negative 3 minus 1 times 1. 2 times negative 3 is negative 6 minus 1, that is negative 7. Next, let us find the inverse of matrix A, that is the reciprocal of the determinant 1 over negative 7 times the matrix negative 3, 2. This is from the main diagonal of the original matrix. The elements are swapped or switch, negative 3, 2. And in the other diagonal, we get the negative of the elements. We have negative 1, negative 1. Performing the scalar multiplication, negative 1 over 7 times negative 3, that will be positive 3 over 7. Next element, we have 1 over negative 7 times negative 1, that is 1 over 7. In the second row, we have 1 over negative 7 times negative 1, 1 over 7. And then the last element in the second row, 1 over negative 7 times 2, that is negative 2 over 7. And then finally, we'll get the values for x and y. That is the variable matrix xy equals the inverse of A multiplied by the constant matrix negative 25, 138. Let us do that. 3 over 7 times negative 25 is negative 75 over 7 plus 1 over 7 times 138, that is 138 over 7. Second row, 1 over 7 times negative 25 is negative 25 over 7. Negative 2 over 7 times 138, that is 276 over 7. Simplifying the elements of this column matrix, that is the solution to x and y, we have negative 75 plus 138 is equal to 63 divided by 7, that is equal to 9. In the other element, negative 25 minus 276, that is 301, or negative 301 divided by 7, that is negative 43. So the solution to the variable matrix xy is the column matrix 9, negative 43. Therefore, x is equal to 9 and y is equal to negative 43. The numbers are 9 and negative 43. That will be all. Thank you for watching. Please subscribe for more math lessons.